Imagine you are looking at a quiet patch of night sky that has barely changed for millions of years. A few faint galaxies, some scattered stars, nothing special. Then, suddenly, that darkness erupts with a flash so bright it outshines an entire galaxy, rises to peak in just a couple of days, and fades again almost before anyone can point a telescope at it. It is bluer than most explosions we know, so hot and intense that it seems almost unreal. It does not behave like our familiar supernovae, the grand deaths of massive stars that we thought we understood. It is as if the universe has fired a cosmic flare gun that does not match any of our usual rules. And once astronomers saw one of these impossible flashes, they started finding more. The deeper they looked, the clearer one unsettling question became. What if some of the brightest explosions in the universe are not what we thought at all? For more than a century, we have told ourselves a comforting story about stellar death. Massive stars are born, burn through their fuel in a few million years, and then die in predictable ways. Sometimes they collapse and rebound as core collapse supernovae. Sometimes they detonate in white dwarf binary systems. The details are complicated, but the broad picture felt solid. We could look at a spectrum, measure how the light brightened and faded, and slot an explosion into a familiar category. It felt like we had a good handle on the most powerful stellar bangs the cosmos could throw at us. Then, starting in 2018, that feeling began to crack. Astronomers started talking about a new kind of event with a clumsy but revealing name. Luminous, fast blue, optical transient. Luminous because these things are absurdly bright, rivaling the glow of billions of suns. Fast because they reach peak brightness and fade away much more quickly than ordinary supernovae. Blue because their light is dominated by very high temperatures. Optical transient because they pop up in visible light for a short time and then vanish. Each word in that name is a clue to the mystery, and together they signal that something very strange is happening. If you have heard of a supernova before, you might picture a star gently swelling, then suddenly tearing itself apart in a vast spherical blast. The core collapses under gravity, the outer layers rebound and explode, and a shockwave races out through the surrounding gas. In a textbook sketch, the explosion is roughly round, energy pours out evenly in all directions, and the light curve follows a familiar rise and fall over weeks. Astronomers have spent decades creating detailed models that match these curves. When we talk about the life and death of stars, supernovae are our reference point. The luminous, fast blue optical transients refuse to fit that template. They rise too quickly, often in a couple of days instead of the week or two that a normal supernova takes to reach its peak. They are far brighter at maximum light, in some cases 100 times brighter than a typical core collapse explosion. Then they fade away almost as quickly as they appeared. When astronomers take spectra of these events, breaking the light into its component colours, they see features that hint at powerful engines buried inside, rather than a simple expanding cloud. The first of these events hit the headlines in 2018. It happened in a relatively nearby galaxy, and it was given a dry catalogue name based on the date and coordinates. The last 3 letters just happened to spell a simple, everyday word: cow. Astronomers love a good nickname, so they leaned into it. The cow was bright, blue, and fast. So much so that it set off alarms in automated survey systems. For a moment, it looked like an unusually energetic supernova. That would have been interesting enough. But within days it was clear that the cow was not playing by the normal rules. Its light rose to an astonishing peak and then dove rapidly, as if someone had cranked up a cosmic dimmer switch and then suddenly turned it down again. Radio telescopes and X-ray observatories joined the chase. They saw signs of a compact central source still pumping out energy long after the initial flash, something that looked more like a newborn black hole or a hyperactive neutron star than a star that had simply blown itself apart and gone dark. Instead of a neat spherical shell drifting away, the cow seemed to be blasting matter and radiation out in preferred directions, a messy aspherical explosion. If you picture this event as a crime scene, the clues were everywhere. and none of them quite matched the profiles in our existing police files. The brightness suggested a huge amount of energy released in a small region. The blue colour and the rapid evolution hinted that the material was extremely hot and diffuse, rather than a thick, slowly cooling shell. The persistent high-energy emission suggested that something compact at the centre was still at work, driving shocks into the surrounding gas. To fit all that into our supernova models, astronomers had to push parameters to the edge of plausibility. At first, many researchers argued that the cow was just an extreme example of a known class. Maybe it was a massive star that had shed a dense shell of gas shortly before exploding. When the core collapsed and the shockwave ripped through that shell, the collision could convert kinetic energy into light very efficiently, giving a short, bright flare. Or perhaps we were seeing a jet driven by a newborn black hole punching its way out of the star, somewhat like the gamma ray bursts we already knew, but seen from a different angle and in different wavelengths. These were not wild guesses. They were careful attempts to extend existing theory just far enough to cover the new data. Yet the unsettling feeling remained. This was a single event. It could be a freak, a cosmic oddball. One weird outburst is an invitation to speculation, but it is not proof that you need a new category. To know whether you are dealing with a new kind of explosion, you need a sample. You need to know if the universe is throwing these things at us regularly, or if the cow was a once-in-a-century oddity. That doubt hung in the air as the first flurry of papers came out. Was this really a new class? Or would it quietly fade into the background of supernova stories? The universe did not leave us waiting for long. In the same year, and then again a couple of years later, all sky surveys caught more flashes that looked uncannily familiar. They were just as blue, just as fast, just as luminous. They were given their own catalogue names, and once again astronomers pulled playful nicknames from the random letters. A koala, a camel. Soon the community started grouping them together in talks and papers, using the term luminous fast blue optical transient as if it had always been there. Now a pattern began to emerge. These events tended to occur in the spiral arms of galaxies, right in or near regions where stars are still forming. That is exactly where you would expect to find very massive, short-lived stars. Those giants live fast and die young, and they do not have time to wander far from their birth clusters before they explode. So the locations of these explosions made sense if they were somehow linked to the deaths of massive stars. On that point, the luminous, fast blue optical transients seemed to be shouting their origin system at us. But the detailed behaviour still pushed back against simple labels. The rise times, the peak brightness, the colours, and the persistent high-energy radiation all stretched our core collapse models. It was as if the universe had taken the familiar script for how a big star dies and scribbled new, more dramatic lines across key pages. Every time we tried to fold these flashes neatly into the supernova category, some piece of data stuck out at an awkward angle. If you and I zoom out for a moment, we can see why this is such a big deal. Stars are the factories that build the elements in our bodies. The way they live and die shapes the chemistry, the structure, and the habitability of galaxies. When we discover a new type of stellar death, we are not just collecting exotic fireworks, we are learning about how black holes are born, how the heaviest elements get mixed into space, and how energy flows through the cosmos. Every luminous, fast blue optical transient is a hint that we might be missing a chapter in the story of how the universe evolves. Catching these events is hard. They are brief visitors on the stage of the sky. A typical luminous, fast blue optical transient might rise and fade over a week, sometimes even less. If your telescope is not looking in the right direction at the right moment, you simply miss it. That is why surveys that repeatedly scan large areas of the sky have become so important. Robotic observatories take rapid images of the same regions night after night, looking for anything that changes. When the software spots a new point of light or sudden brightening, it sends out automatic alerts that trigger a global scramble. You can imagine the experience from an astronomer's point of view. One moment you are sorting through routine alerts, another supernova, another variable star, another asteroid. Then a new entry appears on your screen. It is brighter than expected, bluer than most, and its brightness is climbing unusually fast. You run a quick comparison with archival images, and there was nothing there just days before. At that moment, you have to decide whether to spend precious telescope time chasing it. Do you drop everything and turn your instruments toward this newcomer? Or do you assume it is a mundane flare that will soon fade into obscurity? The first teams who chased the cow and its blue, fast cousins made the risky choice. They called observatories on different continents, spun up radio arrays and X-ray satellites, and poured hours into watching a single point of light evolve. Their gamble paid off. The data they collected turned a curious blip into a whole new case file. It also set off a wave of friendly competition. Each new event became a race to see who could measure it first, who could pin down its host galaxy, and who could model its physics. Through all this, a working theory started to take shape. Many researchers lean toward the idea that luminous, fast blue optical transients are a rare kind of core collapse explosion. A massive star collapses, forms a compact object in its core, and launches jets that punch through the stellar envelope. In some angles and energy ranges, these jets produce gamma-ray bursts, those terrifying flashes of high-energy radiation. In others, especially when the jets interact with dense shells of previously ejected gas, they might produce the bright, blue, short-lived optical flares we are seeing. In other words, the luminous, fast blue optical transients might be the messy, sideways cousins of the famous gamma-ray bursts. It is a tempting story. It ties the new phenomena to things we already know. It explains the locations in star-forming regions and the enormous luminosity. It makes testable predictions about how many of these events we should see and how their light should evolve. For a while, it looked like we were converging on a neat explanation. You can feel the pull of that neatness. We like it when mysteries fit into existing narratives. It makes the universe feel knowable. But if you have been following along, you might already feel a nagging doubt. The universe has a habit of giving us just enough data to build a beautiful theory, and then throwing in a new observation that tears it apart. The same telescopes that caught the cow, the koala, and the camel were still watching when two even stranger explosions lit up the sky. One in a galaxy where it should not have behaved the way it did, and one far outside the crowded star-forming disks altogether. These would challenge every assumption lurking quietly in that neat story. The moment you give a new kind of cosmic explosion a name, you are really doing two things at once. On the surface, you are just describing what you see, a bright blue flash that fades quickly in visible light. Underneath, you are quietly promising that the chaos is starting to make sense, that there is a pattern solid enough to deserve a label. Luminous, fast blue optical transient sounds dry, but it carries a kind of hope. It tells you and me that these are not random freak events. They are members of a family, and families have origins and rules we can in principle understand. To see how that confidence grew, we have to go back to the first member of the family, the cow, in 2018. It did not appear in a dramatic Hubble image or a carefully planned pointing. It showed up as a line in an automated alert stream from a survey telescope that spends its nights scanning the sky for anything that changes. In this case, the telescope was part of the Atlas project, a system designed to spot potentially dangerous asteroids. Instead, it caught a different kind of hazard, an explosion in a distant galaxy that was simply too bright to ignore. Within hours, the new object had a provisional classification. Its spectrum looked roughly like a Type 1b core collapse supernova, the kind that happens when a massive star has lost its outer hydrogen envelope before dying. The host galaxy seemed ordinary enough. The brightness was shocking, but not impossible if you pushed your models hard. On that first night, it was easy to tell a simple story. Somewhere in that galaxy, a very massive star had reached the end of its life. Its core had collapsed, and its outer layers had been blasted into space. Then the universe refused to cooperate. The light curve, the way the brightness changed with time, did not follow the usual script. Instead of taking a week or more to climb to peak luminosity, The cow shot up in just a couple of days. Instead of fading gracefully over a month, it dropped like a stone. Observers who switched to radio and X-ray eyes found that the new source was still blazing away at high energies, even as its optical light declined. That is not what a simple, symmetric supernova remnant does. That is what a compact engine does when it keeps dumping energy into its surroundings. If you picture an ordinary core collapse supernova, you can imagine a roughly spherical shockwave racing outward through the star and then into the surrounding gas. The explosion is certainly messy on small scales, full of instabilities and clumps, but when you pull back and look at the whole thing, it is reasonably round. Light leaks out through that expanding shell in a predictable way. The cow did not look round in that deeper, physical sense. Its emissions seemed to be shaped by something directional, perhaps a jet, perhaps a lopsided cloud of material nearby. As more telescopes locked on, the list of oddities grew. The spectra lacked some of the lines you would expect in a normal Type 1b supernova at that stage. The temperature inferred from the colour was incredibly high, hotter than most expanding shells managed to stay for long. The radio emission suggested that the shockwave was ploughing into a medium that was either unusually dense or arranged in a strange way. Piece by piece, the neat initial classification peeled away, and astronomers started cautiously calling the cow a luminous fast blue optical transient instead. For a short time, many teams did lean toward that explanation. Perhaps the cow was a massive star that had burped off a thick shell of gas just years before collapsing. When the supernova shock slammed into that shell, it could have converted kinetic energy into light with outrageous efficiency, giving you the short, bright optical flare. Or perhaps this was a star that formed a black hole at its core and launched narrow jets that just barely escaped, not enough to make a classic gamma-ray burst, but enough to energize the surrounding matter. Both pictures kept the cow in the comfort zone of stellar death. The real test of any theory, though, is whether it survives new data. One weird explosion does not force you to change your textbooks. Two that look very similar start to raise eyebrows. Three make people talk about a new class. Only a few months after the cow, skies on the other side of the planet produced that second case. This time it was the Zwicky Transient Facility in California and its wide-field camera that caught the flash. The basic story was déjà vu. A sudden, blue, extremely bright point of light in a star-forming region of a distant galaxy, rising and fading faster than a typical supernova. This second event carried its own bureaucratic catalogue number, but the community quickly gave it another animal nickname. When a third similar explosion appeared in 2020, again in a star-forming spiral arm, the trend was impossible to ignore. Now we had a small zoo of luminous, fast blue optical transients, each one a shocking flare in a galaxy rich with young, massive stars. Locations were a big part of the case file. All three of these early events came from inside the bright, star-forming disks of their host galaxies, often in or near the spiral arms. That matters because the most massive stars live fast and die young. They form in dense clusters of gas and dust, burn through their fuel in a few million years, and explode without ever wandering far. If you see a violent explosion smack in the middle of a spiral arm, your first instinct is to blame a recent massive star. It is simple, and it fits what we already know about where core collapse supernovae happen. There were other supporting clues. Some of the observed elements in the ejector hinted at massive star progenitors. The overall energies involved, while extreme, could be squeezed out of a collapsing core if you allowed for an unusually strong engine and special circumstances. If you were determined to keep the luminous, fast blue optical transients inside the supernova family, you had plenty of material to work with. Over conference coffee and late-night video calls, researchers sketched variations on the theme: jet-driven explosions, stars wrapped in multiple shells of previously ejected gas, magnetars spinning near breakup speeds. You and I might be tempted to think that with that much brainpower, the problem would be solved quickly. Yet every time a model matched the gross features of the data, small details refused to line up. a bump in the light curve that arrived too early, a colour that stayed too blue for too long, a radio signal that implied shock velocities that were hard to reconcile with a simple expanding shell. These friction points did not kill the supernova idea, but they kept it from feeling fully satisfying. This is a subtle kind of tension that happens a lot in science. Outwardly, the community might speak in confident phrases about a preferred model. Inwardly, the people who have stared longest at the data feel nagged by inconsistencies. They know that if they overcommit to a tidy explanation too early, the universe has a way of embarrassing them later. So they keep dual tracks running in their minds. On one track, luminous fast blue optical transients are a rare yet natural extension of core collapse supernovae. On the other, they are a sign that something else, perhaps something fundamentally new, is happening when massive stars die. Meanwhile, the sky does not stop. Survey telescopes keep sweeping their rectangles of heaven, night after night, building up rivers of data. Many of the alerts that come out of those systems are mundane, like known variable stars or ordinary supernovae glowing peacefully in far-off galaxies. Buried among those thousands of events are the few that do not fit the templates, the ones whose light curves look just a bit too quick, a bit too blue, a bit too bright. Spotting those oddballs is where the real fun begins. One of the clever things astronomers have done in recent years is teach computers to help find those outliers. Luminous fast blue optical, transient, luminous fast blue optical, transient appears. Those systems sometimes recognize its signature fast rise and blue color before human eyes do. That early warning buys precious hours to swing sensitive instruments into position and catch the event in its brief, most revealing phase. As these tools improved, the sample of luminous fast blue optical transients slowly grew. Each new member of the family offered a chance to check whether the emerging theory held up. Did it occur in a star-forming region? Did it show evidence of dense surrounding gas? Did its light evolve in the same broad way as the others? For the most part, the answers were yes, or at least close enough to keep the working picture alive. At the same time, the stakes kept rising. If luminous fast blue optical transients really are the signatures of newborn black holes, or magnetars chewing their way out of collapsing stars, then they are not just curiosities. They are direct glimpses of the engines that power some of the most extreme phenomena in the universe. They could tell us how often those engines form, how efficient they are at launching jets, and how they feed energy back into their host galaxies. In a way, each new event is a live experiment that nature is running for us, at energies we will never reproduce on Earth. It is worth pausing here to ask yourself a simple question. If the universe were trying to tell us that we have misunderstood something basic about how massive stars die, would it send one lonely, ambiguous outburst? Or a whole set of explosions that share a name, a cluster of traits, and just enough misbehaviour to keep theorists awake at night? The luminous, fast blue optical transients feel very much like that second kind of message, a pattern that hints at deeper rules we have not written down yet. By the early 2020s, review talks and papers started to include sections on these events. Plots showed clusters of points representing ordinary supernovae, and then a separate island of luminous fast blue optical transients sitting off to one side, higher in brightness and shorter in timescale. The working narrative went something like this. These are likely unusual core collapse explosions in very massive stars with dense circumstellar environments, perhaps involving jets or rapidly spinning magnetars. It was a mouthful, but it made people feel they had a handle on the problem, at least for now. If our story ended there, it would be neat and satisfying. We would close the case by stamping these flashes as rare but understood and move on. Yet even as that consensus was forming, the universe was already preparing the next twist. All it had to do was produce an explosion that looked like a luminous, fast blue optical transient at first glance, but then evolved in a way that no one had anticipated. An event that refused to be a single, clean outburst, and instead seemed to hiccup, flashing again and again as if some hidden engine was stuttering. That was the moment when the neat story of luminous, fast blue optical transients began to unravel, and when astronomers realized they might be dealing not with one new family of explosions, but with several. When astronomers first saw the light curve of that new outburst, it looked like a practical joke. The initial flash was everything they had come to expect from a luminous, fast blue optical transient. A blinding blue rise in brightness, a peak reached in a matter of days, then the beginning of a sharp decline. Observatories all over the world shrugged, labelled it another member of the growing zoo, and moved on to the next tasks in their queue. Then, minutes later, the same patch of sky flared again. Same rough brightness, same colour, same position. It was as if the universe had hit replay on an explosion that should have been a one-time event. That was the first hint that this was not just another blue flash, but something stranger. Over the following hours, the outburst, now nicknamed the Tasmanian Devil, refused to die cleanly. Instead of fading away like its cousins, it kept pulsing. Short, sharp bursts of light stacked one after another, separated by only a few minutes. Each pulse was not a weak echo, but a blast as bright as the original flare, as if some hidden engine were disgorging packets of energy, again and again, with frightening regularity. If you plot that behaviour on a graph, brightness on the vertical axis, time on the horizontal, the result does not look like the smooth hill of an ordinary supernova. It looks like the jagged skyline of a city, spike after spike punching upwards from a baseline. Behind each spike is a real physical process. Something out there, 3 billion light-years away, was switching on and off in a way that no one had seen before at this scale. Naturally, the first instinct was to suspect a mistake. When an effect is this unprecedented, you have to rule out the boring explanations before you let your imagination near it. Could the detector have glitched? Was there a software artifact that was being misread as repeated pulses? Did some calibration error turn a single flare into a series of fake ones? The history of astronomy is full of famous false alarms that turned out to be human fingerprints on the data. This time, the safety net held. Independent telescopes in different countries, using different instruments, all saw the same pattern. The Tasmanian Devil really had pulsed at least 14 times that we know of, and probably more when no one was looking. Each pulse packed more energy than hundreds of billions of suns emit in the same brief interval. It was not a software hiccup. It was the sky. If you think back to how we have studied stars and supernovae up to now, you can feel why this is so unsettling and so tantalizing. Most of our understanding of stellar life cycles comes from seeing different objects that happen to sit at different stages. A red giant here, a young massive star there, a supernova remnant somewhere else. We assemble those snapshots into a timeline in our minds, but we almost never get to watch a single object move through a complex sequence in real time. The Tasmanian Devil dangles the possibility of a different kind of story. A star or compact object that seems to die, then brighten again, then again, as if we are watching a slow-motion tug-of-war between gravity and whatever forces are trying to hold the system up. If that is what is happening, then buried inside that light curve is a movie of stellar death written in real time. At first, some astronomers tried to fold this bizarre behaviour back into the core collapse picture. Perhaps the collapsing star had multiple shells of material around it. The shock wave from the first explosion might slam into one shell, flare, then punch through and hit another, flare again, and so on. Or maybe the central engine, a newborn neutron star or black hole, was gulping down matter in bursts. Each gulp could briefly power a jet or an outflow that showed up as a pulse. These ideas kept the Tasmanian Devil roughly within the walls of the massive star story. Nothing in its location or its basic spectrum absolutely ruled that out. It seemed to sit in a region where big stars could have lived. Its colours and energies, though extreme, did not directly violate core collapse theory. You can almost feel the community trying to keep the family together. Yes, this child is wild, they said, but it is still one of ours. Then came the Finch, and the family resemblance shattered. On a night in April 2023, surveying cameras picked up yet another bright blue flash. At first blush, it ticked all the usual luminous fast blue optical transient boxes: extremely luminous, rapid rise and decay, blue emission. For a few crucial hours, it looked like a normal member of the strange new club. Teams began to file the usual reports. Another one. Add a point to the pattern. As more data came in, something was wrong in a way that no one had anticipated. When astronomers traced the position of the Finch back to deep images of its region, they expected to see it overlaying a spiral arm, or at least the fuzzy glow of a galaxy. Instead, they found almost nothing. The explosion did not sit in the disk of a galaxy at all. It floated in the darkness between two galaxies, about 15,000 light-years away from the nearest one we could see. If you try to picture that, imagine looking at two distant islands in the night, each dotted with the lights of cities. Now imagine a lightning bolt that flashes in the ocean between them, far from any land. If you knew that lightning normally starts above land, because that is where storms live, you would have a problem. What is driving a storm in the empty sea? That is roughly how the Finch looked to astronomers who had become used to linking luminous, fast blue optical transients with massive stars. Big stars do not live between galaxies. They form in clusters inside galaxies, in regions rich in gas and dust. They do not have billions of years to wander off into intergalactic space. They live fast, die young, and die close to home. So if the Finch was a massive star collapsing, it was doing so in the one place it absolutely should not be. That single fact hit the core collapse model like a wrecking ball. Either the explosion was not caused by a massive star, or our understanding of where those stars live and die needed radical surgery. When a leading theory takes a hit like that, you can almost hear the mental gears shift. Researchers stopped asking which flavour of massive star collapse could make a Finch, and started asking something more radical. What kinds of engines can live, or be flung, into the outskirts of galactic halos, and then produce a luminous, fast blue optical transient when they finally meet their fate? Two broad possibilities rose to the top. The first involved a kind of black hole that sits in a frustrating gap in our observations. We have strong evidence for black holes a few times to a few dozen times more massive than our Sun, the remnants of individual stars. We also have overwhelming evidence for supermassive black holes with millions or billions of solar masses sitting quietly, or not so quietly, in the centres of galaxies. But the intermediate range, black holes with 100 to 10,000 solar masses, remains tantalising and largely theoretical. If these intermediate mass black holes really exist, one of the places they might lurk is in globular clusters. These are dense, ancient balls of stars that orbit in the halos of galaxies, far above and below the main disk. A single globular cluster can contain hundreds of thousands of stars packed into a region just a few dozen light-years across. They are like beehives hanging in the outskirts of a galactic garden. It is possible that some globular clusters harbour a heavyweight in their centres, an intermediate mass black hole that has quietly grown by swallowing stars. In computer simulations, stars that stray too close to such a black hole can be captured into tight, highly elongated orbits. With each close pass, the black hole's tidal forces strip more material from the star, stretching it into a stream and heating it until it glows. After a few of these deadly orbits, what remains of the star is finally torn apart completely and flung out at a significant fraction of the speed of light. A sequence like that could, in principle, make a very bright, very fast flare. It could easily live in the outskirts of a halo, far from the visible disk of any galaxy, because that is where globular clusters live. If the Finch went off in such a cluster, we might not see the host cluster directly in our images yet, but we would be seeing the final act of a long dance between a star and a hidden intermediate mass black hole. You can feel the appeal of this explanation. It uses an engine that theorists already want to exist for other reasons and places it in an environment where such engines are expected to live. It explains why the Finch was so far from any obvious galaxy and why its energy output was so high. It also offers a testable prediction. If we push our telescopes harder, especially in infrared light, we might eventually spot a faint globular cluster at the Finch's position, giving the intermediate mass black hole idea a serious boost. The second possibility that rose quickly in the discussion involved another kind of exotic engine. Instead of a single black hole tearing up a star, what if the Finch was produced by two compact objects spiraling together? A pair of neutron stars, or a neutron star and a black hole, could wander out into a galactic halo over billions of years. When they finally meet and merge, they release a furious blast of energy. We already know that such mergers can power some of the brightest explosions in the universe. When neutron stars collide, they can trigger a killer nova, a brief but intense flash of light, powered by radioactive heavy elements being forged in the debris. These mergers also send out gravitational waves, ripples in space-time, that instruments like the Laser Interferometer Gravitational Wave Observatory are built to detect. If the Finch was a compact object merger, then the luminous, fast blue optical transient would be the light half of a double message. The other half would be a gravitational wave signal passing through Earth around the same time. Catch both, and the case would be very strong. Annoyingly, the timing could not have been worse. When the Finch went off in April 2023, the major ground-based gravitational wave observatories were offline for upgrades and maintenance. There was no sensitive ear listening to space-time in that moment. If a beautiful chirp of gravitational waves did wash through our solar system from the direction of the Finch, no one was there to capture it. That silence is not evidence against the merger idea. It is simply a missing data point. We also did not detect a strong gamma-ray burst from the Finch, which you might expect in some merger scenarios. But remember, this explosion happened about 3 billion light-years away. At that distance, and depending on the direction of any jets, the gamma-ray signal could simply have been too faint or too misaligned for our detectors to notice. So the Finch sits there, in our mental sky, refusing to commit to one story. It might be the death scream of a star torn apart by an intermediate mass black hole in an unseen globular cluster. It might be the optical counterpart of a neutron-star merger that we fail to hear in gravitational waves. It might even be something we have not yet imagined, some hybrid process that combines elements of both. What matters most for our story is that it exists at all. The Finch proves that luminous, fast blue optical transients are not confined to the bright disks of galaxies. At least some of them are happening out in the dim, sparsely populated halos, or even in the true intergalactic medium. That alone is enough to shatter the comforting idea that all of these flashes are just weird supernovae. Whatever powers them has to be able to live or travel far from the crowded nurseries of massive stars. In a way, the Tasmanian Devil and the Finch form a pair of puzzle pieces that do not quite touch. One shows us an engine that refuses to explode just once, instead pulsing again and again in a rapid sequence, as if something at its heart is stuttering. The other shows us an explosion divorced from any obvious birthplace, suggesting engines that can wander or hide in the outskirts of galaxies. Together, they push luminous, fast blue optical transients away from the safe centre of our supernova models, and into a much wilder landscape of compact objects and deep gravitational wells. If you imagine yourself in the shoes of the scientists working on this, you can feel the tug from two sides. On one side is the desire for a clean classification. We like to put things in boxes and write down simple rules. On the other side is the growing suspicion that nature is mixing several different engines under one set of observational traits. Maybe some luminous fast blue optical transients are powered by newborn magnetars inside collapsing stars. Maybe others are tidal disruptions caused by intermediate mass black holes. Maybe a few are mergers, cousins of the kilonovae we already know. How do you tell those stories apart when all you see at first is a bright, fast blue flash? Light carries some of the answers. Spectra, colours and timing can all hint at the composition and geometry of an explosion. Location offers powerful clues as well. An event in a spiral arm is more likely to be a massive star death. One far out in a halo leans toward compact object scenarios. But as the Finch reminds us, light alone can leave too much ambiguity. To really untangle these mysteries, we need another messenger, a way to sense not just the glow of an explosion, but the invisible violence in its core. That is where a different kind of observatory enters the story. One that does not care whether the sky is cloudy or clear, or whether an event happens in the crowded disk of a galaxy or in the empty stretch between them. It listens not for photons, but for tiny tremors in the fabric of space-time itself. And the first time it heard a signal clearly, it rewrote our map of the most extreme collisions in the universe. Before we built machines that could hear it, the universe looked strangely quiet. We saw distant galaxies colliding in slow motion and supernovae blooming like cosmic flowers. But all of that drama played out in light alone. When the Laser Interferometer Gravitational Wave Observatory finally recorded its first clear signal, it was as if someone turned on a soundtrack that had always been there. The same universe suddenly felt denser, more violent, more alive. If luminous, fast blue optical transients hinted that we were missing a chapter in the story of stellar death, gravitational waves told us we had been missing an entire sense. The idea behind these waves goes back to general relativity, which says that mass and energy do not just sit in space, they shape space and time themselves. A massive object like a star or a black hole curves the space-time around it. When two such heavy objects orbit each other and then collide, they do not just move through this curved fabric, they stir it. That stirring sends out ripples, tiny stretching and squashing of distance that travel outward at the speed of light, spreading through the universe the way ripples spread across a pond after a stone falls in. Those ripples pass through us all the time. Pairs of distant black holes and neutron stars emerging in far-off galaxies right now, their gravitational waves sweeping across Earth, quietly stretching and compressing everything by an amount far smaller than the width of a proton. The reason you do not feel this is simple. The effect is unimaginably small. It is like trying to notice if the distance between New York and Los Angeles changes by less than the width of a human hair. Yet if you could measure that tiny change, you would be listening directly to some of the most extreme events the universe can produce. That is what the Laser Interferometer Gravitational Wave Observatory was built to do, and why it had to be as unforgivingly precise as human engineering could manage. At its heart, each detector in this observatory is surprisingly simple to describe. Take a powerful laser and shine its beam down a long vacuum tunnel that extends for several kilometers along the ground. At the intersection, split the beam into two parts and send each down a different arm at right angles to each other. At the far ends of those arms, hang mirrors that reflect the beams back toward the intersection, where they recombine. If the two arms have exactly the same length, the returning light waves line up in a specific way and produce a stable pattern when they overlap. Now imagine that a gravitational wave passes through this giant letter L. As the ripple moves by, it stretches space very slightly in one direction and compresses it very slightly in the perpendicular direction. One arm effectively becomes a little longer, the other a little shorter. The light rattling back and forth between the mirrors takes a slightly different time to travel each path. When the beams recombine, the pattern shifts. By monitoring those shifts with absurd precision, the observatory can tell when space itself has flexed. That description fits into a few sentences. Turning it into reality took decades of work and a willingness to fight noise on every front. The vacuum tunnels have to be among the emptiest places humans have ever created, so that air molecules do not scatter the light. The mirrors have to be polished so perfectly that any tiny imperfection could masquerade as a signal. The suspensions have to isolate those mirrors from passing trucks, distant earthquakes, even changes in local temperature and air pressure. On top of that, every other wobble of our planet has to be understood and filtered out. Lightning strikes, wind gusts, human footsteps in control rooms, all of those can jostle the apparatus enough to mimic a gravitational wave if you are not careful. It is like trying to hear the faint chirp of a bird in a stadium while 100,000 people are cheering. You do not just need a good microphone. You need a way to recognize the exact pattern of the bird and ignore the roar. That is one reason why there are two main detectors in the Laser Interferometer Gravitational Wave Observatory, one in Washington State and one in Louisiana, separated by thousands of kilometers. A real wave passing through Earth will stretch space at both sites in almost the same way, with a tiny delay. Local noise like a passing truck will not match up. If both detectors record the same strange pattern at nearly the same moment, the odds that it is a real wave go up dramatically. For a long time, the detectors heard nothing but the stadium noise. The initial version ran for years with no confirmed detections. That was not a failure in the scientific sense. It set important limits on how often certain kinds of collisions could happen. Still, it was hard not to feel the tension. Had the world of compact object mergers turned out to be quieter than hoped? Were the waves even weaker than expected from the theory? Instead of giving up, the collaboration upgraded. The second generation, often called Advanced Laser Interferometer Gravitational Wave Observatory, pushed the sensitivity down by roughly an order of magnitude. That does not sound like much in everyday terms, but in this field it meant listening to a volume of space hundreds of times larger. Suddenly, many more potential collisions were within reach. In September 2015, only days after the upgraded detectors began collecting data, a pattern appeared. It was short, less than a second long, a smooth rise in frequency and amplitude that matched what theorists had predicted for years. Two black holes, each roughly a few tens of times more massive than the Sun, spiraling together and merging into one. The ripples from that final plunge had crossed more than 1 billion light years to gently jiggle the arms of our detectors by less than the width of a proton. You could take that pattern, translate it into sound, and it would rise in pitch as the black holes orbit faster and faster before they fuse. To many people in the field, hearing that sound for the first time was an emotional moment. It was direct evidence that these binaries existed, and that general relativity's description of gravity still held under extreme conditions. Perhaps even more striking, that first event left almost no trace in light. No obvious gamma-ray burst, no bright flare in visible wavelengths. If you had been looking at that region of the sky with ordinary telescopes, you might have seen nothing. The universe had whispered a secret that only our new gravitational sense could hear. That set the tone for what followed. Over the next few observing runs, the detector network, joined by sister instruments in Europe and Japan, picked up dozens of mergers. Most were pairs of black holes. A few involved at least one neutron star. Every signal added a point to a new kind of map, one that charted the masses, spins, and frequencies of the most compact objects in the cosmos. These observations already changed the way we think about how stars live and die. Some of the black holes were more massive than we expected from normal stellar evolution alone, suggesting unusual pathways for their formation. Some mergers happened in environments that would have been hard to infer from light-based data. We could now measure how often such collisions happen, which in turn informs how often certain elements are made and how much energy is being pumped into galaxies through these violent processes. If you look back at our earlier puzzle, luminous, fast blue optical transients like the Finch, you can see why this matters. Light-based data left us with multiple overlapping stories that could explain the same flash. From stars being shredded by intermediate mass black holes, to compact object mergers. A gravitational wave detection happening at the same time and from the same direction would pick a winner. It would tell us whether the central engine was a collision between compact bodies or something else entirely. The power of having both light and gravitational waves together became crystal clear in August 2017. On that day, the detector network caught a longer, lower frequency signal that did not look like the now familiar black hole mergers. Models matched it to two neutron stars spiraling inward. Just seconds after that gravitational wave signal peaked, a burst of gamma rays arrived from the same patch of sky. Telescopes around the world snapped into action, and over the next hours and days they watched a new point of light bloom and change colour. That glow, known as a kilonova, carried the fingerprints of heavy elements forming in real time. For decades we had suspected that elements like gold and platinum were forged in the extreme conditions around neutron star mergers, This single event made that suspicion feel much closer to settled fact. The gravitational waves told us that two neutron stars had collided. The light showed us the radioactive decay of freshly minted heavy nuclei. Together they turned a textbook diagram into an observed reality. Try to imagine what that means as a viewer. You are no longer just watching a distant flash. You are reconstructing, almost step by step, what happened inside. Two dense stars, the size of a city but more massive than the sun, spiraled together, smashed, and threw out matter that then rearranged itself into the elements that might one day sit in a wedding ring or a computer chip. Both messengers, space-time ripples and light, carried complementary pieces of that story. This is why many astronomers talk about multi-messenger astronomy as a new era rather than just a new technique. Light, across all its wavelengths, remains a rich source of information, but it is sensitive mostly to the surfaces and debris of events. Gravitational waves carry information from the deep interior of systems that are completely opaque to light, like the last few milliseconds before two black holes merge. Together, they turn distant catastrophes into well-constrained physical experiments. There is another, quieter benefit as well. Gravitational waves do not care if an event happens in a luminous galaxy or a dark one. They sweep through intergalactic space without being absorbed by dust or gas. That means they are an ideal probe of environments like the outskirts where the Finch exploded. A merger out there might be almost invisible in light, but its tremors in spacetime would still ring clearly in our detectors, at least in principle. For now, our listening is still intermittent. The detectors must shut down for upgrades and maintenance. They have limited sensitivity and can only catch events above certain strength thresholds. That is why the Finch produced such frustration. If it was produced by a merger, its gravitational waves would have been exactly the thing to tell us. Yet when it went off, the instruments we needed were quiet for very human reasons. You can feel the urgency in the community today as they race to increase the sensitivity and uptime of this network. Each new observing run covers more volume, from more directions, with better localization. For events that do produce both light and waves, that means faster alerts, better sky maps, and more precise constraints on the physics. For events that only whisper in gravity, it means a chance to discover entire populations of dark explosions we have never seen. The connection back to luminous, fast blue optical transients is not just speculative curiosity. If even a fraction of these blue flashes are powered by compact object mergers, then a joint detection would tie together several threads at once. It would tell us how often such mergers occur in different environments, how much energy they deposit in surrounding gas, and how that might relate to the production of heavy elements. It would also help to pin down whether there really are intermediate mass black holes lurking in the halos of galaxies, as some Finch models suggest. On the flip side, gravitational waves also tell us where certain ideas are unlikely. If we observe a luminous, fast blue optical transient with no accompanying gravitational signal during a period when the detector network is fully up and sensitive to that region, we can begin to rule out some merger scenarios and lean harder on stellar collapse or tidal disruption explanations. In that sense, silence can be as informative as a shout. All of this points toward a future in which we will not think of an explosion as either a light event or a gravitational wave event. Instead, we will think of it as a single physical process that sends out multiple kinds of signals, some of which we can catch and decode. Each new instrument we bring online, each upgrade that pushes the noise floor lower, is like adding another microphone to a complex concert. Now imagine combining that new sense with what we have already learned from the brightest bursts of electromagnetic radiation alone. There is a special class of explosions that have tested our theories for decades, blasts that outshine entire galaxies in gamma rays for brief moments. One of them, recorded recently, was so intense that it saturated our instruments and cast a measurable shadow in Earth's own atmosphere. It is nicknamed the brightest of all time. If luminous fast blue optical transients are the strange blue cousins of ordinary supernovae, these gamma ray events are their wild, high-energy siblings. They are the places where jets, magnetic fields, and particle physics all collide. And as we will see, They do not just threaten our understanding of stellar death, they force us to question what kinds of engines can exist inside collapsing stars, and whether some of the particles they throw out might be windows into new physics entirely. When astronomers talk about the most violent things the universe can do to ordinary matter, they almost always end up talking about gamma-ray bursts. These are not steady glows. They are sudden, needle-thin flashes of the highest energy light we know, turning on and off in seconds or minutes. For a brief time, a single gamma-ray burst can outshine every other source of high-energy radiation in the observable universe. For decades, we knew they were out there, but they were comfortably far away, so distant that their wildness felt abstract. Then, in late 2022, something happened that changed that feeling. A single burst went off at just the right distance and in just the right direction, and it was so bright that instruments around Earth practically screamed. Gamma-ray bursts come in two broad flavours. The short ones, which last less than about 2 seconds, are usually linked to the mergers of neutron stars or neutron stars with black holes. The long ones, which can last from a few seconds to a few minutes, are mostly tied to the collapse of very massive stars that form black holes and launch jets. Both types are intense, but for our story, the long bursts are the key. When a massive star collapses, it does not always blow itself apart evenly. Sometimes it funnels a huge fraction of its energy into two narrow jets that punch through the dying star and blast out into space at nearly the speed of light. Those jets are why gamma-ray bursts are so bright. Imagine the difference between a normal flashlight and a laser pointer. The flashlight spreads its light in all directions, so any one spot is only softly illuminated. The laser concentrates its light into a narrow beam, so whatever it hits looks dazzlingly bright, even if the total energy is modest. Gamma-ray bursts are the cosmic version of that laser. If one of those jets happens to point almost exactly at us, the burst looks far brighter than it would if the energy were spread evenly in all directions. Most of the gamma-ray bursts we have seen so far are not only tightly beamed, they are also very distant, billions of light years away. That distance acts like a safety cushion. The bursts are still absurdly energetic, but by the time their light reaches us, it is spread out enough that our detectors can record them without being overwhelmed. They are powerful, but they live in a part of the universe that feels safely remote. In October 2022, that cushion shrank. Space-based observatories detected a gamma-ray burst from a galaxy only about 2 billion light-years away in the constellation of Sagittarius. 2 billion light-years sounds unimaginably far, and it is, but by the standards of gamma-ray bursts, it is surprisingly close. That small difference in distance made a huge difference in how bright the burst looked to us. It was so intense that some instruments saturated, registering only that something was off the charts. Very quickly, astronomers started calling it by a nickname that captured its status: the brightest of all time. The burst had a technical catalogue name, but the short phrase stuck because it was accurate. In our entire history of watching the high-energy sky, we had never seen anything like it. For weeks after the initial flash, telescopes sensitive to X-rays and gamma rays continued to record an afterglow that refused to fade the way most bursts do. If you happened to be on Earth that day with no special instruments, you would not have seen anything with your eyes. Gamma rays cannot pass through the thick layers of our atmosphere, but the atmosphere itself noticed. The burst was so strong that it ionized particles high above our heads, measurably disturbing the ionosphere on the side of Earth that faced the event. A flash of energy from 2 billion light-years away physically changed a layer of our planet's air. That alone would have made this burst a landmark. It was a reminder that the universe is not just a distant show. Events out there can, in a small but real way, reach in and touch the environment we live in. But the more astronomers studied the brightest of all time, the stranger it became. One set of observations came from X-ray telescopes that watched the region around the burst for days and weeks. Instead of seeing a simple fading point of light, they saw expanding rings. Those rings were not actual shells of matter rushing outward from the explosion. They were echoes. The original burst had scattered off layers of dust inside our own galaxy. Each ring corresponded to gamma rays bouncing off a particular dust cloud at a particular distance. That echo pattern let astronomers map the structure of the Milky Way along that line of sight in a way that had never been possible before. A distant catastrophe had turned into an exquisitely precise probe of the dust between stars. Another set of observations came from instruments designed to catch the very highest energy gamma rays, particles carrying trillions of electron volts. Those detectors recorded an unexpectedly large number of extreme energy photons from the burst. To understand why that is weird, you have to picture the space between galaxies not as perfect emptiness, but as a thin fog of starlight and infrared glow called the extragalactic background light. In theory, when a very high-energy gamma ray travels through this fog, it should bump into those background photons. When that happens, both particles can transform into an electron and its antimatter twin, a positron. The upshot is that the universe should be kind of opaque to the most energetic gamma rays over long distances. Yet from this burst, which came from billions of light years away, we saw more extreme energy photons than expected. It was as if some of the gamma rays had slipped through the cosmic fog more easily than our models allow. Not only had the brightest of all time saturated our detectors, it had quietly raised a question about how transparent the universe really is to the most energetic light. Working backwards from the afterglow, astronomers tried to figure out what kind of engine could power such a burst. At first, many thought that the underlying supernova must have been extraordinarily massive, perhaps a star dozens of times more massive than the Sun, collapsing in a way we had never seen before. When the light from the accompanying supernova finally emerged from the glare, though, it looked surprisingly ordinary. The star that died to make this record-breaking burst was not especially enormous. It was the way it died, and the way the jets were aimed, that made the difference. One possibility is that the jet in this burst was much narrower than in typical gamma-ray bursts. Remember the laser and flashlight analogy? If you take the same amount of power and squeeze it into a narrower beam, anything in that beam will see a brighter flash. If the jet in the brightest of all time had an especially tight opening angle and happened to line up almost perfectly with our line of sight, then even a fairly standard collapser could look extraordinary. That explanation helps with part of the puzzle. It fits the idea that long gamma-ray bursts are beamed and that observed brightness depends strongly on viewing angle, but it does not fully solve the problem of the extreme energy photons that seem to travel farther than expected without being absorbed by the background light. To address that, some theorists have suggested that the burst might be pointing toward a gap in our understanding of particle physics, rather than just astrophysics. One of the more intriguing ideas involves hypothetical particles called axions, or axion-like particles. In many versions of modern physics, axions are extremely light particles that interact very weakly with ordinary matter. They were originally proposed to solve a problem in the theory of the strong nuclear force, but they have also become popular as potential dark matter candidates. If axions exist, they can sometimes mix with photons in the presence of strong magnetic fields. A gamma ray could convert into an axion, travel through space ignoring the usual sources of opacity, and then convert back into a gamma ray near us. In that picture, the brightness and the unexpectedly high number of extreme energy photons in the brightest of all time would be a hint that some of the gamma rays took a detour through an axion state. It is a clever way to get around the cosmic fog problem without tearing up the underlying cosmology. Of course, it is also speculative. We do not have independent proof that axions exist, and many other explanations are still on the table, including refinements to our models of the background light and the microphysics inside the jet. Even if axions never show up, the fact that a single gamma-ray burst can push on questions about dark matter shows you how powerful these events are as natural laboratories. The temperatures, densities, and magnetic fields inside the jet are so extreme that they are far beyond anything we can create on Earth. By watching how the burst evolves across different wavelengths and energies, we indirectly watch physics being tested in regimes that would otherwise be totally inaccessible. There is another thread woven into this story, one that loops back to the heavier elements we use in jewelry, electronics, and even medicine. We already saw that when neutron stars merge, They can forge elements like gold and platinum in the swirling debris around them. But collapses, the massive star collapses that power long gamma-ray bursts, are also in the running as factories for heavy elements. In some models, as the outer layers of the star fall toward the newborn black hole, some material is flung out in neutron-rich winds. Those winds can host the same rapid neutron capture process that builds up heavy nuclei. The brightest of all time, then, was not only an absurdly luminous lighthouse in our sky, it may have been part of the cosmic production line that seeded its host galaxy with the ingredients for future planets and perhaps future life. Somewhere in that distant galaxy, atoms of gold fashioned in the chaos of that collapse might one day end up locked in rocks or flowing in the cores of giant planets. When you think about it that way, gamma-ray bursts become more than destructive fireworks. They are part of how the universe recycles matter into ever more complex forms. For you and me, it is hard not to feel a mix of awe and unease as we put these pieces together. On one hand, bursts like the brightest of all time are rare, and most of them happen far away. On the other hand, we have just seen direct evidence that even at a distance of billions of light years, a single burst can nudge Earth's atmosphere. That prompts a natural question. What if something like this happened much closer? What would it do to a planet and to anything living on its surface? Astronomers have started to take that question seriously, not out of morbid curiosity, but because it connects high-energy astrophysics to the history of life. There are hints in Earth's geological record that distant supernovae have already dusted our planet with radioactive isotopes in the past. Some people have even proposed that a gamma-ray burst pointed roughly in our direction could have contributed to one of the mass extinctions in deep time, though that idea is still debated. What we know for sure is that supernovae and gamma-ray bursts release enough energy to strip away atmospheres, damage ozone layers, and bathe surfaces in ionizing radiation if you get too close. The exact danger zone depends on many details, from the type of explosion to the structure of the magnetic field around the planet, but we can start to draw rough boundaries. Inside a certain radius, life as we know it would be in serious trouble. Outside it, the effect might be limited to subtle isotopic traces and small changes in atmospheric chemistry. Having just seen the brightest gamma-ray burst in recorded history shake our ionosphere from what is still a comfortably large distance, we have a fresh motive to pin those boundaries down. In the next part of our journey, we are going to put you right next to a dying star, and then slowly move you outward, asking at each step how survivable the blast would be. Along the way, we will meet some famous candidate stars in our own sky, and ask whether any of them are close enough to keep us awake at night. Imagine standing on a planet that orbits a bright blue giant, a star dozens of times more massive than your sun. For millions of years, it has been a reassuring presence in the sky, hot and steady, pouring out light that warms your world and shapes its seasons. Then, in a single night, everything changes. The star brightens until it outshines all others combined. Then its surface tears itself apart as a shockwave rips outward through its interior. A blast of light, X-rays and gamma rays surges across space, followed by a slower storm of high-energy particles. If you could watch from that planet's surface, you would be seeing not just a beautiful spectacle, but the end of the environment that made life possible. The same physics that creates heavy elements and recycles matter into new stars would, at that distance, sterilize everything. To understand how close is too close, we first need to be clear about what a supernova actually is. For massive stars, the story begins when they exhaust the nuclear fuel in their cores. As long as fusion is running, the outward push of energy balances the inward pull of gravity. Once iron and similar elements build up at the center, fusion stops paying its energy bills. Gravity wins. The core collapses inward in a fraction of a second, slamming into nuclear densities. That sudden halt and rebound drive a shockwave back out through the star, blasting the outer layers into space at thousands of kilometers per second. That is one main route to a supernova, the collapse of a single massive star. There is another path for lower mass stars in close binary systems. In those, a white dwarf can pull material off a companion until it reaches a critical mass and ignites runaway fusion in its whole interior. The result is a thermonuclear disruption of the white dwarf itself. Both types unleash energies so vast that numbers almost lose meaning. In a few weeks, they can emit as much energy as an ordinary star like the Sun does over billions of years. What matters for life is not the total energy though, but how much of it reaches you. Three main hazards emerge from these explosions. First is the flash of high-energy radiation, especially X-rays and gamma rays, which arrives at the speed of light. Second is the flood of charged particles and cosmic rays that arrive later as the blast wave plows through surrounding gas and accelerates material to extreme speeds. Third is the longer-term impact on the structure of the interstellar medium around a planetary system, which can strip, compress, and reshape gas and dust in ways that influence future star and planet formation. If your planet orbits the star that explodes, the story is simple and grim. At those distances, even modest supernovae can strip away atmospheres, destroy ozone layers, and heat surfaces enough to boil away oceans or melt rock. Anything surviving underground would have to contend with a long reign of high-energy particles. In practice, planets that close are almost certainly lost causes once the progenitor star reaches the end of its life. The more interesting question for us is what happens when the explosion is on the sky, not under your feet. When astronomers talk about danger zones for life elsewhere, they often focus on what the high-energy radiation would do to a planet's atmosphere. Ozone is particularly vulnerable. A sudden dose of gamma rays and X-rays can split nitrogen and oxygen molecules, triggering chemical reactions that destroy ozone and create nitrogen oxides. With ozone thinned or gone, more ultraviolet light from the host star reaches the surface, increasing mutation rates and damaging biological molecules. Models suggest that a supernova within a few tens of light years could cause a severe ozone depletion event on an Earth-like planet. The exact safe distance is fuzzy and depends on the explosion's energy, the spectrum of its radiation, the orientation of any jets, and the properties of the planet's own magnetic field and atmosphere. Roughly speaking, if a core collapse supernova goes off within about 10 light years, the radiation dose would be catastrophic for complex life on the surface. Are 100 light years away? Models are 100 light years away. Models indicate that the impact on ozone and surface conditions is much more modest, though still potentially detectable in subtle chemical markers. Gamma-ray bursts tighten those numbers. Because their energy is beamed into narrow jets, the intensity along the beamline is far higher than in an ordinary supernova. A long gamma-ray burst pointed directly at a planet within a few thousand light years could, in principle, cause dramatic ozone loss even without destroying the planet outright. Fortunately, the odds of both a burst happening that close and its jet being aimed exactly at you are extremely small. The galaxy is large, and the number of directions a jet can point is enormous. As you and I sit here, it is natural to ask whether Earth has ever taken a hit from these kinds of events. The rocks and fossils under our feet carry clues. In ocean sediments and in ferromanganese crusts on the sea floor, scientists have found traces of an isotope called iron 60, which has a half-life of about 2.5 million years. That isotope is not produced in significant quantities by ordinary geological processes on Earth. It is, however, made in the cores of massive stars and ejected in supernova explosions. The layers where iron 60 spikes show up correspond to times a few million years in the past. The most straightforward interpretation is that one or more supernovae exploded within perhaps 100 light years of Earth during that period, sprinkling their debris across our solar system. The amounts are small, but their presence is like a fingerprint. Combined with models of how dust and gas move through the galaxy, they suggest that our local region of space has been shaped by a series of supernovae over the past 10 to 20 million years. That picture fits with another piece of evidence, the so-called local bubble. When astronomers map the distribution of gas around the Sun, they find that we sit in a cavity of relatively low density. Radio and X-ray data indicate that the walls of this cavity are made of denser, hotter gas, as if a series of overlapping supernova blasts had carved out a bubble in the interstellar medium. Our solar system is drifting through the interior of that bubble right now. In a sense, you and I live in a neighborhood that bears the scars of past explosions. If those events happened within 100 light years or so, why are we still here? One answer is that distance matters. The closer supernovae were probably near the outer edge of the dangerous zone, enough to leave chemical traces and perhaps nudge climate conditions without sterilizing the planet. Another answer is time. Life is remarkably resilient, and the fossil record shows that ecosystems can recover from even severe shocks given a few million years. That does not mean the effects were trivial. Some researchers have suggested that nearby supernovae might have contributed to climate shifts by altering cosmic ray flux and cloud formation, or by modestly thinning ozone and increasing ultraviolet exposure. There are even proposals linking such events to specific minor extinction or turnover events in the fossil record. These ideas are intriguing, but not yet settled. What they do show clearly is that once you think in terms of millions of years, stellar explosions are part of the background environment for life in a galaxy like the Milky Way. When we narrow our focus to human timescales, however, the question shifts from, has this ever happened, to, will it happen soon? That is where names like Betelgeuse and Antares enter the conversation. Betelgeuse is the red supergiant that marks the shoulder of Orion in your night sky. It is bloated, unstable, and clearly nearing the end of its life. Astronomers know from its size, temperature, and mass that it will eventually explode as a core collapse supernova. Antares, the red heart of Scorpius, is another aging giant destined for a similar fate. Betelgeuse is roughly 600 light-years away. The exact distance has some uncertainty, but it is safely above the ranges where we worry about catastrophic atmospheric damage on Earth. If it were to explode tomorrow, it would outshine the full moon and be visible in the daytime sky, but the high-energy radiation at our distance would be heavily diluted. It would not strip away our ozone layer or fry electronics. Antares is even farther out. These stars represent an opportunity rather than a threat, a chance to witness a nearby supernova in real time with modern instruments. There are other potential supernova progenitors closer than Betelgeuse, including certain massive stars in nearby clusters, but none we know of are close enough to pose a serious risk in the foreseeable future. Surveys of massive stars in the local neighborhood, combined with models of their life cycles, suggest that the rate of truly dangerous events within about 30 light-years of Earth is very low over the next few million years. That is not zero, but it is low enough that other risks, including our own technological choices, dwarf it on human timescales. Gamma-ray bursts have their own list of potential sources, notably certain types of rapidly rotating, metal-poor massive stars. Those are more common in the outer regions of galaxies and at earlier cosmic times. Our patch of the Milky Way is relatively metal-rich and older, which makes the conditions for those extreme bursts less favourable here and now. This does not eliminate the possibility of a nearby burst aimed at us, but it pushes it into the realm of long odds stretched over huge times. Thinking in this way changes the emotional weight of these cosmic catastrophes. On the scale of the galaxy, supernovae and gamma-ray bursts are both destructive and creative. They tear apart stars, but they also distribute heavy elements, compress gas clouds, and trigger new rounds of star formation. On the scale of a single planet, they can be deadly. On the scale of human lives and histories, they are part of the background conditions within which we have always lived. If we look beyond our own world, though, their influence could be far more dramatic. Imagine a planet orbiting a star in a densely packed star-forming region, where massive stars are born in close proximity. In those environments, the intervals between nearby supernovae could be short enough that complex life struggles to persist. Atmospheres might be repeatedly stripped and rebuilt. Biospheres might be reset again and again just as they begin to diversify. In quieter regions, like the outskirts of a galaxy, or the calmer suburbs where our sun lives, life might enjoy longer stretches of stability. Some researchers have even speculated that there may be a kind of habitable zone within a galaxy, not just around stars. Too close to the crowded centre, and you risk high exposure to radiation from supernovae and from the central black hole. too far out, and you may not have enough heavy elements to build rocky planets and chemistry-rich environments. Somewhere in between, the odds for complex life might be highest. In that broader view, supernovae are not just threats, they are part of the landscape that shapes which regions of the cosmos can nurture civilizations long enough for them to ask these questions. You can also flip the perspective. Instead of seeing these explosions only as dangers, consider them as signals. A supernova is an unmistakable announcement that a massive star has run out of time. A gamma-ray burst is a flare that says a jet has pierced a collapsing star. For any intelligence watching the sky with even modest instruments, these events are loud markers of where the most extreme astrophysics is happening. They might draw curious minds the way volcanic eruptions draw geologists, or lightning storms draw atmospheric scientists. With that in mind, a strange symmetry appears. While we worry about whether a nearby supernova could harm us, we also use distant supernovae as tools to measure the expansion of the universe. While we picture gamma-ray bursts as potential doom beams, we also use them to map star formation across cosmic history and to probe the gas between galaxies. The same events that could, in rare cases, threaten life on a planet are also some of the best beacons for understanding the universe as a whole. All of this sets up a deeper shift in our story. Until now, we have been looking at natural cataclysms, explosions that follow the impersonal rules of gravity and nuclear physics. The cosmos is noisy enough, even without any deliberate messages. Yet somewhere in this storm of light and radiation, there could be signals of a very different kind. Not the death throes of stars, but the actions of minds. Not just flashes that happen to reach us, but broadcasts or beams that were never meant to be subtle. The challenge is to tell one from the other when all we have are brief, mysterious blips in our detectors. If you strip away the romance, the search for other minds is mostly a war against noise. The universe is overflowing with signals that have nothing to do with intelligence. Pulsars tick like cosmic clocks. Magnetars crack and flare. Black holes and neutron stars merge and ring space-time like a bell. Against that roaring background, any deliberate transmission from an alien civilization would arrive as just another flicker in a data stream, a spike on a graph, a pattern of numbers a computer thinks looks a little odd. The strange part is that many of the traits we would look for in an artificial signal are also produced by some of the wildest natural engines we know. Early attempts to listen for other civilizations were almost endearingly simple. Point a radio dish at a nearby star. Tune it to a quiet part of the spectrum where natural sources are relatively faint. Record the incoming noise and look for a narrow spike, a pure tone that stands out. The idea is straightforward. Nature is messy. It tends to produce broad, noisy signals spread over a range of frequencies. Technology, on the other hand, often produces very sharp, clean tones. Think of the difference between the hiss of wind and the clear note of a flute. If you ever saw that kind of tone coming from a distant star system, it would be hard not to think of transmitters. In the decades since, searches have grown more sophisticated, but the basic logic remains. Look for something that stands out as unnatural. It might be a narrow band tone, a repeating pattern, or a complex modulation. Crucially, it has to survive several rounds of skepticism. Is it coming from the sky rather than from our own technology? Does it repeat in a way that is consistent with a distant source moving with the motion of its star and planet, rather than with our orbit and rotation? Does it show the signature of having travelled through interstellar plasma, a kind of frequency-dependent smearing called dispersion that affects natural and artificial signals alike? The history of this field is littered with almosts, signals that, for a brief moment, look like they might be the one, only to fall back into the pile of human interference or subtle natural phenomena. One recent example came from observations of Proxima Centauri, the nearest star to our Sun. As part of a survey that listens to nearby stars across a wide swathe of radio frequencies, a narrow band signal popped up near the direction of Proxima that did not immediately match any known satellite or terrestrial transmitter. It sat in a relatively clean part of the spectrum. It persisted for several hours. It was given a dry label, but in the hallways and online discussions, people called it something more evocative: a candidate. For a while, that candidate sat in a curious limbo. It was not obviously fake, but it was not obviously real either. Teams dug into the data looking for patterns. They checked whether the signal appeared only when the telescope pointed at Proxima, or also when it looked elsewhere. They examined its frequency drift, which could betray whether the source was on Earth, in orbit, or truly interstellar. All of this took time and care. If you rush, you risk fooling yourself. If you are too slow, you risk letting excitement fester into myth. In the end, patient analysis did what it usually does. The signal turned out to be a kind of subtle interference from human technology, probably something on or near the telescope site that was drifting in frequency in a way that happened to mimic an interstellar origin. It was not a message from Proxima. It was a reminder that our own machines are louder in our ears than the universe is. An older, somewhat legendary case followed a similar arc, was narrow in frequency and appeared more than once. It was given an awkward alphanumeric name that later became something like a campfire story in the community. People speculated about alien beacons, deep space radars, or exotic natural mazes. Over the years, as instrumentation improved and better monitoring of interference was put in place, that signal slowly lost its mystique. Reanalyses pointed strongly toward human origin, a quirk of the way the receiver and local electronics interacted. These false alarms are not failures, they are training exercises. Each one forces us to sharpen our tools for distinguishing our own technological noise from the sky. They also show how modest the threshold is for excitement. All it takes is a signal that is narrow, persistent, and a bit unexpected, and our pattern-seeking brains begin to sketch transmitters and civilizations. Meanwhile, nature has been quietly generating its own strange radio flashes, and for a long time we did not even notice them. In 2007, an astronomer sifting through old data from a telescope in Australia found a single bright radio pulse that lasted just a few milliseconds. It was too short and too intense to be a typical pulsar or known burst. It also showed strong dispersion, meaning that lower frequency components arrived noticeably later than higher ones. That is exactly what you would expect if a pulse had travelled through a deep column of intergalactic plasma. The event seemed to have come from far beyond our galaxy. That lonely pulse was the first fast radio burst anyone recognised. At the time, it was easy to wonder if it might be artificial. A millisecond flash from beyond the Milky Way with no obvious counterpart at other wavelengths fits nicely into science fiction plots. To be responsible, most scientists kept their speculations grounded. One event is not enough to build a theory. Was it a glitch? Was it a one-off explosion? Or was it the tip of a population we had somehow missed? As more telescopes began to hunt for similar bursts, the sky answered. Dozens, then hundreds of fast radio bursts began to show up. Many were one-time events, a few repeated. One source in a distant dwarf galaxy produced bursts over and over again across months and years, sometimes in clusters, sometimes in quiet spells. The dispersion measures confirmed that most of these sources were at cosmological distances. Whatever was producing them was releasing an enormous amount of energy in a ridiculously short time. Early on, some people floated the idea that advanced civilizations might be using fast radio bursts as beacons or as byproducts of powerful technology, for example by driving giant light sails. It was an attractive notion. The bursts were bright, sharp, and at frequencies where artificial transmitters might operate. But as the sample size grew, natural explanations began to take the lead. Several observations pointed toward magnetars, neutron stars with magnetic fields so intense that they can shake their own crusts and outer layers into violent flares. The turning point came when a fast radio burst was finally caught from inside our own galaxy, from a known magnetar. In 2020, radio telescopes recorded 2 short bursts from a source called SGR 1935. At the same time, space-based X-ray observatories saw a flare from the same object. The energies and timing lined up well with the idea that the radio pulses were generated during magnetar outbursts. That does not mean every fast radio burst comes from exactly that mechanism, but it showed conclusively that at least some are natural. You might think that result would close the door on artificial possibilities. In practice, it does something subtler. It moves the baseline. Once we know that nature can produce millisecond flashes that look for all the world like technological pings, we are forced to raise the bar for what would count as evidence for intelligence. A single fast radio burst, even a repeating one, is no longer enough. We would need additional layers of unnatural structure, such as complex modulation, encoding that resists explanation in terms of known physics, or behavior tied not to the life cycle of stars, but to something like an orbital pattern. This is the recurring theme. As we improve our instruments, the universe keeps filling in the catalogue of exotic but natural signals. Pulsars once looked like lighthouses built by someone. Quasi-stellar radio sources once looked like artificial beacons. Fast radio bursts flirted with that status. Each time, nature has turned out to be capable of more diverse behaviour than we assumed. That does not mean there are no artificial signals out there. It means the burden of proof has grown heavier. There is also a feedback loop between our understanding of catastrophic events and our search for technology. A civilization that wants to send a signal across the galaxy must grapple with the same background we do. Their message would have to ride on top of or dodge around things like supernova remnants, magnetar storms, and bursts from accreting black holes. If they use a natural lighthouse as a carrier, perhaps by modulating a pulsar or amplifying a magnetar flare, their handiwork would be hidden in a very noisy environment. If they use a quiet channel, they must pick a frequency and location where the universe itself is unusually silent. When you imagine aliens, it is tempting to project our own broadcast habits outward. We think of steady television carriers, radar pings, or powerful narrow beams aimed at particular stars. In reality, an advanced civilization might use technologies we would not immediately recognize. They might communicate mostly with tight beams between their own worlds that rarely pass near us. They might prefer optical or infrared flashes instead of radio, or even exploit neutrinos or gravitational waves. From our point of view, many of those possibilities would be effectively invisible. That is one of the reasons some researchers have shifted focus from deliberate messages to techno-signatures, indirect signs of technology. Instead of looking only for a hello, they look for the side effects of industry and engineering, waste heat from giant structures, chemical imbalances in atmospheres that are hard to explain with natural processes, strange temporal patterns in starlight that might hint at megastructures, even anomalies in the statistics of fast transients, if a civilization was somehow using catastrophic events as power sources or timing references. All of this sounds speculative, and it is, but it is anchored in something we can measure. Our own civilization already produces techno-signatures, radio leakage, waste heat, chemical traces in the atmosphere. When we point telescopes at planets around other stars, we are slowly reaching the precision needed to see similar signs if they exist elsewhere. The challenge is always the same: separate signal from noise, separate deliberate design from the wild creativity of physics. Here is where the storms we have been talking about become not just background, but tools. Luminous, fast blue optical transients, gamma-ray bursts, magnetar flares, and neutron star mergers all light up their environments in ways that can reveal the distribution of gas, dust, and magnetic fields. They can also act as flashlights that backlight the atmospheres of any planets that happen to lie along the line of sight. In principle, with enough sensitivity, we could use the brief glow of a distant catastrophe to probe a planet that would otherwise be invisible, reading the fingerprints of its air as the light passes through. You can imagine, a few decades from now, a catalogue that does not just list where the universe has exploded, but also what those explosions have illuminated. A map where each tick mark is a place where we have measured the chemistry of a distant world, looked for imbalances that might hint at life, and searched for subtle anomalies that might hint at technology. In that map, the most violent events become guiding beacons for the most delicate questions. Even if we never find an artificial signal, The process of looking will keep sharpening our understanding of the noisy universe. Every false alarm teaches us something about our instruments or about natural phenomena. Every new class of transient forces us to reconsider our assumptions. By the time we are ready to interpret an undeniably artificial message, we will hopefully have a deep catalogue of everything the cosmos can do on its own. There is an irony at the heart of this. The same explosions that could in theory wipe out a biosphere are also some of the best aids we have for discovering biospheres elsewhere. The same storms that might reset the evolutionary clock on a young world might, from a safe distance, provide the backlighting that lets us watch its atmosphere breathe. If there are minds out there, they too will have grown up in a universe filled with these catastrophes. Their myths and sciences will be shaped by the same violent sky. As we build better ears and eyes, from more sensitive radio arrays to telescopes that can catch the briefest flashes, the line between listening for nature and listening for culture will blur. A single new class of burst might tell us how neutron stars crack. The same burst, seen in a different way, might hint at engineering. The only way to be ready is to keep collecting, keep comparing, and keep asking whether we are missing a pattern that is hiding in plain sight. In the end, whether the next strange signal we catch is natural or artificial, it will widen our sense of what is possible. A new kind of explosion tells us something about physics. A true technosignature would tell us that our story is not unique. Either way, the sky will feel less like a static dome and more like a living, changing network of events. And the next time a surprising flash or ripple appears on our screens, we will not just ask what happened out there, but what it might reveal about the deep workings of reality itself. Right now, as you listen, new instruments are being assembled in deserts, on mountaintops, deep underground, and even in orbit, all with one shared goal. They are trying to catch more of those brief, impossible flashes we have been talking about before they fade. The luminous fast blue optical transients, the gamma-ray bursts, the magnetar flares, the mergers that shake space itself. Each new detector is like another sense we are bolting onto our species. If you picture the universe as a crime scene filled with clues, these machines are the forensic tools that let us dust for fingerprints on scales that make galaxies look small. On a Chilean mountaintop, one survey telescope in particular is being built to change our view of the dynamic sky. It will scan the entire visible southern sky again and again on a timescale of days, building a time-lapse movie of everything that changes. Stars that brighten and dim, asteroids that drift, supernovae that flare and fade, and those rare, blue, ultra-fast outbursts we still barely understand. Instead of relying on chance, we will be watching almost all the time. If you imagine that for a moment, you can see how the numbers change. Today, luminous, fast blue optical transients are precious. We know only a handful well. With a full sky time-lapse running for 10 years, the sample will grow from a zoo of a few strange animals into a catalogue of hundreds or thousands. The shapes of their light curves, the locations in their host galaxies, the distribution of their energies will all be mapped in detail. Patterns that are invisible in a small sample will start to pop out. That is when some of our guesses will be tested hard. If some of these events are powered by newborn magnetars in massive stars, their statistics should track star-forming regions closely. Fraction emerges. Their delay times, fraction emerges. Their delay times from star formation should look different again. You and I will be able to ask the sky directly which engines are actually at work. At the same time, on another front, engineers are slowly quieting every source of noise in the gravitational wave detectors. Better mirrors, better lasers, better suspensions. Each incremental improvement means a larger chunk of the universe becomes audible. The volume of space from which we can hear black holes colliding grows as the cube of that reach. Double the sensitivity, and suddenly there are 8 times as many events within range. In a few years, those observatories will be joined by a new generation of detectors built in different places on Earth and eventually by a giant interferometer in space, with arms millions of kilometers long trailing our planet around the sun. That space-based instrument will be sensitive to slower, deeper ripples, the kind produced by pairs of massive black holes as they spiral together over hours and days, or by compact objects orbiting very close to supermassive black holes. It will turn the low bass notes of the universe into something we can literally chart. Put those developments together and you begin to glimpse what the next few decades of cosmic forensics could look like. A bright, fast flash appears in a distant galaxy. Almost at once, survey telescopes flag it as a candidate luminous, fast blue optical transient. Within minutes, an alert goes out. Gravitational wave detectors cross-check their data streams for any ripples from the same direction and time. X-ray and gamma-ray satellites swing around to stare. Radio arrays listen for a fresh source. Sometimes the answer will be no. No gravitational waves, no high-energy counterpart, just the optical flare. That negative result is itself a clue. Other times, everything will light up at once. A chirp in space-time, a flash in gamma rays, a blue optical spike, a radio afterglow. Each messenger will carry a different piece of the story, and for the most extreme events, we will not have to guess which engines are involved. We will see them from the inside out. This kind of multi-messenger choreography will not be limited to big explosions, nearby magnetars that cough and crack, white dwarf stars that collide in quiet corners of galaxies. Even the steady hum of thousands of small black hole binaries across the universe will show up as a background signal in the data. The more carefully we learn to subtract and classify this natural noise, the easier it will be to spot anything that refuses to fit. There is another kind of cosmic forensics unfolding at the same time, focused not on the engines themselves, but on what their light passes through. Every photon that reaches us from an explosion has travelled through gas, dust, and sometimes the atmospheres of planets on its way. It picks up tiny imprints of that journey, absorption lines from hydrogen and heavier elements, subtle dimmings and colour shifts from dust. If the path crosses a planet at just the right angle, a faint fingerprint from that planet's air. This is where the future of exoplanet science gets tangled up with the study of cosmic catastrophes. As new space telescopes and giant ground-based observatories come online, they will be able to split the light from distant transits and flares into spectra with incredible precision. In those spectra, they will look for oxygen that is out of chemical balance, methane paired with oxidized gases, complex molecules that hint at biological activity. They will also look for species that are difficult to produce without industry, like certain combinations of nitrogen oxides, chlorofluorocarbons, or exotic pollutants. Explosions can help by acting as backlights. A supernova in a galaxy rich with planets may briefly illuminate the atmospheres of several worlds along our line of sight. A gamma-ray burst may backlight interstellar clouds and any systems hidden behind them. Detecting those tiny signals will be hard, but not impossible. It turns the most violent deaths of stars into temporary flashbulbs for planetary portraits. If you think about that, it is a strange twist. The same events that can strip atmospheres from nearby worlds become tools for studying the atmospheres of others at safe distances. Catastrophe and insight, bound together by the path of light. On the more speculative edge, some teams are beginning to ask how we might use all this new sensitivity to search for technologies beyond our own, not by expecting a clear hello in a narrow radio channel, but by looking for anomalies in the statistics of many events. Do some stars dim in ways that hint at engineered structures rather than dust? Do some planets show industrial chemicals that cannot easily be explained away by volcanoes or weird geochemistry? Do some transients repeat with clock-like regularity that does not match any known engine? We might never find such things. Or we might find one anomaly that survives every attempt at a natural explanation. If that happens, a lot of what we have built to study explosions will be repurposed on the spot. The same wide-field telescopes, the same radio arrays, the same gravitational wave detectors. They will all become parts of a planet-scale observatory network, trying to watch a single impossible event from every angle. Even if no techno-signature ever appears, the journey toward that sensitivity pays off in other ways. To be able to say with confidence that a signal is not artificial, we first have to understand all the things it could be naturally. That forces us to build better models of stellar evolution, better simulations of jets and shocks, better reconstructions of element formation. The search for other minds becomes, almost by accident, a way of sharpening our picture of a mindless universe. There is also one more frontier coming into focus, a frontier inside the fundamental laws themselves. The brightest gamma-ray bursts, the most extreme luminous fast blue optical transients, the closest neutron star mergers, all push matter and radiation into regimes where quantum physics and general relativity are both important. In those regimes, tiny deviations from our current theories might show up. Small changes in how fast certain particles propagate, slight shifts in the energies at which photons begin to disappear, unexpected patterns in gravitational waveforms. Every time we record a burst like the brightest of all time and find more very high-energy photons than expected, we are nudging at those edges. Every time we match a gravitational wave signal to the predictions of our equations and find no discrepancy, we are tightening the leash on new physics. At some point, perhaps in the light curve of an especially weird explosion or in the detailed ringing of a black hole, we might see the first crack. If that happens, it will feel a lot like the first time luminous fast blue optical transients appeared on our screens. A pattern that cannot be pushed into any existing box without breaking the box. The difference is that this time, the new pattern would not just be about how stars die, it would be about how space, time, and matter themselves behave at their limits. You might wonder where all this leaves us, tiny creatures on a small world orbiting an ordinary star. Does learning about more ways the universe can explode make our existence feel more fragile or more meaningful? In a way, it does both. When you realize that our local region of space has been carved by ancient supernovae, that our atmosphere carries faint fingerprints of past blasts, and that the atoms in your bones were forged in earlier generations of dying stars, it becomes hard to see yourself as separate from these events. You are part of the aftermath. At the same time, the very fact that we can talk about luminous fast blue optical transients and gamma-ray bursts and gravitational waves means we occupy a strange and rare niche. We are made of matter that has been through all those cycles, yet we are also able to build instruments that reach back along those cycles and decode them. The universe is studying itself through us, in the same way it might one day study itself through someone on another world. As new detectors switch on and new surveys start sweeping the sky, you and I are living through a moment when the universe is about to look very different. The quiet regions will turn out to be full of subtle tremors. The rare flashes will turn out to have cousins we never suspected. Some mysteries, like the origin of heavy elements or the true nature of most luminous fast blue optical transients, will move from the realm of debate into the realm of measured fact. Others will take their place. The next impossible flash that appears in a patch of sky we thought we knew well might force us to admit that some engines are stranger than even our expanded imagination allowed. It might give us the first convincing signature of an intermediate mass black hole, or the first clear sign that axion-like particles exist, or a hint of an entirely new force. It might, just possibly, carry the unmistakable imprint of deliberate structure, a pattern that says there is someone else out there watching their own sky and wondering if anyone will ever notice. When that happens, whether it is a natural revelation or a cultural one, the universe will not have changed. It will be the same cosmos it has been for billions of years. What will change is our story about it. What we think is possible, what we think is likely, and what we think our place is inside that large, restless hole. For now, we keep listening. We keep watching for the sudden blue flare in a nearby spiral arm, for the brightest burst our detectors can handle, for the faintest ripple in the fabric of space. We build better ears and better eyes and better ways of comparing what we see. And somewhere above us, in a sky that looks quiet to the naked eye, the next clue is already on its way, racing toward us at the speed of light and the speed of gravity, carrying a message about how reality really works.